So at the end of last time we were looking at this particular game here, this sharing game. The question is, what are the Nash equilibria in here? So let's look at some of these ones. The sort of obvious Nash equilibria is that Andy shares, and so Nash equilibria here requires a policy. So a policy here requires what Barb's going to do. So it actually turns out the Nash equilibrium here, Andy gets to choose one of these things. So for example, Andy's sharing and Barb's saying yes, but we also have a Nash equilibrium as we've got to work out what Barb would do in other situations as well. So it could be Barb would say no here, yes here, and yes here. Turns out that's a Nash equilibrium. No, yes, yes. So neither of them is prepared to deviate from this policy. So this policy here says Barb says yes here, Barb says no to this. So Andy's not going to decide to keep because then Andy gets 0, 0. So if you look at this one here, if Andy says to keep, then it's not in it. So both Barb saying no is actually, turns out to be part of a Nash equilibrium. Well, Barb could say yes as well because that's equally bad to Barb of saying no. The only time that Barb would be incentivized is to say yes is if Andy's either going to share or give. Okay, so there's lots of Nash equilibrium in here. So for example, if Andy keeps, then there's all possibilities for Barb of probability distributions over actions because they're all 0, so they're all Nash equilibrium. If Andy has a probability of sharing, anytime Andy has a probability of sharing, then Barb is going to say yes because that's their Nash equilibrium given that Andy is going to share. Similarly, if Andy is going to give, then it's going to be this. So if you have any non-zero probability here, then it's better for Barb to say yes to here, so Andy is going to be better off to do this as long as Barb says no here. If Barb says yes here, it's in Andy's job to keep sharing. Alright, so Nash equilibrium here is a policy for Andy which says to keep, share or give, but Barb has to choose a value for each of these. Okay, so in here Barb can do anything. We don't know what the value here is. It's somewhere between 0 and 2, and Barb says yes, no here. So presumably it's in Barb's interest to say no here because that forces Andy to either share or give, because it means that it's not really in Andrew's interest to keep it all, because then they do 2. If Barb has a probability of saying yes, then Andy's got an incentive to say keep. Alright, so now let's look at an alternative of this. What if the 2-1 payoff was 1.9, 0.1? So Andy's going to say, well, what I'm going to do is I'm going to choose to keep, but I'm going to pay Barb a little bit. I'm going to bribe Barb a little bit in order so that I can keep. And then it turns out there's a unique Nash equilibrium. So at this point here, Barb has an incentive, right? So Barb is better off, saying yes here. So Barb has a better off going looking here. So this one here, this 2-1 is now 1.9, 0.1. 0.1 is bigger than 0. So Barb has an incentive to say yes. And as soon as Barb says yes, Andy has an incentive to keep. Because then there's only one Nash equilibrium. So it's not obvious that that's the best thing for Barb to do. Barb should maybe say, well, I'm still going to not say no if you decide to keep because I want to share it. Right, so it turns out that this one here, the 1.90, and saying this a unique policy here of keeping and sharing, backing up is what's called a subgame perfect equilibrium. So it's an equilibrium, so that's an equilibrium here and equilibrium here. However, the equilibrium of Andy saying, if Barb's saying no here and yes here is also a Nash equilibrium, in which case Andy's entitled to share. But Andy might think, well, if you get to this point here, if I get to keep, then Barb is going to choose this. Barb is going to choose the 1.9, 0.1. Okay? So if you do backing up here, you find that there's a unique value here. Even though there are multiple Nash equilibrium, there's only a unique value that you get from backing up this value. But it's not obvious that Barb should do this. It's not obvious that Barb should do this, agree to do that, as opposed to saying, I'm going to say no here to force Andy to share. Okay, so that's sort of one example of where, people might think, oh, there's some terrorist that's threatening to me, but if I don't give it into them, then there's not the incentive to blow everyone up, so they're not going to do it. But so you could think that they're rational, and then they lose. But if you think they're irrational, then oh my goodness, they might blow everyone up. Then you might give them money. So it turns out sometimes to be an advantage to be irrational, to appear to be irrational, so you're prepared to blow yourself up if people don't give you things. Okay, so sometimes sort of this is not necessarily the thing we want to do. All right. So in some sense here, the argument is that Barb here shouldn't be rational in the sense of just trying to maximize her expected utility, but should somehow be unpredictable of saying, well, maybe Barb's going to say no, even though it's in her interest to say yes, because at this point here, to force Andy to share. Okay. All right. So now let's look at some computations. To compute a Nash equilibrium for a game in strategic form, what we're going to do is we're going to eliminate dominated strategies. Those strategies that are dominated by other strategies we can remove. Okay, so we can remove any strategy that is dominated by other strategies, so the agent's never going to do it. And it could be the case that they're going to be dominated by a randomized strategy. Then we're going to determine which actions have non-zero probabilities. This is called the support set. So we're going to have the support set here as those actions that have a non-zero probability as a support set. And then we're going to deform the probabilities for the actions in the support set. And so that's for the best way to compute the Nash equilibrium. Is you're going to eliminate dominated strategies, determine which actions have a non-zero probability, and that's the support set. And we're going to determine the probability for the actions in the support set. Turns out the second one of these is actually the hardest one. All right, so let's have a look at an example here. So we can look at these three actions here. So, so I'm going to so if you look at these actions here, there's agent has a choice of three. Agent one gets to either choose A1, B1, or C1, and agent 2 gets to choose either D2, E2, or F2. And here are the payoffs here. And now we can look at the domination here, and one could say, agent 1 can look at this and say, well, let's have a look at this. Well, agent 1 here, let's look at A1 and B1. Well, agent 1, it's sometimes better to choose A1, but sometimes here it's better to choose B1. So neither of those are dominating. But let's look at A1 versus C1. Well, no matter what D1 chooses, so 2 is less than 3, 4 is less than 5, and 1 is less than 2. So no matter what agent 2 does, it's better for agent 1. Agent 1 would never choose C1, so we can cross this one out. Okay? Because agent 1 is never going to choose, if agent A1 is available to it, it's never going to choose C1 because A1 is always better. Okay? Now we might try that for agent 2, and you find out that it's not really, this one's 5 and 1 versus 2, and 1 and 2 versus 9 versus 4. Well, agent E2 is sometimes the best, and D2 is sometimes the best. But it turns out that if you have a randomized strategy, it's 50-50 between D1 and E1, then that's going to have an expected payoff of 5 plus 1 divided by 2 is 3, and this has a 1 plus 9 of 5. So it turns out that F2 is also dominated by a randomized strategy between D2 and E2, so we can remove F2. And now we can do this again. Now the best action for A1 has been rejected because they can't get this 6, and we can see that the B1 is also dominated by A1. Okay, and now we can look at agent 2's point of view. Their 5 is better than the 1, so they're going to reject this. And this one here turns out to be the only Nash equilibria. So we're going to just remove actions that are dominated by something else. And even if they're dominated by a randomized strategy, as F2 is dominated by a randomized strategy. All right, so that's eliminating dominated strategies, but sometimes you don't end up with with a simple one. All right, so now let's suppose we're given a support set, which is a set of actions we're going to randomize through. You can think about why would an agent randomize between actions A1 to AK? Right? Well, why would it do that? Well, the only time it would do that is if it can't decide between them. And the only reason it can't decide between them is if they have to have the same utility. So the only time you're going to randomize between actions A1 to AK is if actions A1 to AK have the same value for that agent given the strategies for other agents. So the only time we're going to randomize is when we have the same value for this. And this actually forms a set of simultaneous equations where the variables are probabilities of the actions. So we're going to solve this set of simultaneous equations to work out which randomized strategy is going to work. So if there is a solution where all the probabilities in the range are 0 to 1, there's a Nash equilibrium. This is a Nash equilibrium. So it turns out that sometimes the values computed are outside 0, 1, and it's no longer a Nash equilibrium. And we're going to then search over support sets to find a Nash equilibrium. So that's how it's going to work. So we're going to eliminate dominated strategies. We're going to search over support sets to find a Nash equilibrium. And now we know how to find a Nash equilibrium. So let's give in this. Here's our probability of a goal. We're going to compute this Nash equilibrium. So this is the same example we saw before. Remember, there was this cyclic thing. So the answer is, when would the goalkeeper randomize? So the goalkeeper would only randomize if the value of kicking left is equal to the value of kicking right. Sorry, jumping left and the value of jumping right. So the probability of a goal given jumping left has got to be equal to the probability of goal jumping right. That's the only time the goalkeeper would possibly think of randomizing. Okay, so let's work out this. The probability of a goal given jumping left depends on the probability that the agent kicks right. So the agent's going to give a goal given they jump left. Well, it's 0.3 times the probability the kicker kicks right, plus 0 times 6 times the probability the agent kicks left. And that's going to equal the probability of a goal given they jump right, which is the agent kicks right with probability 0.9, or the probability to kick left with probability 0.2. So that's the probability of goal given they jump right, depends on the probability of the kicking. And now this is just one equation with one unknown Kr, and we can solve that pretty easily. We can move all the Krs to one side and we end up with a value of 0.4. And so then it turns out to be, this is the unique Nash equilibrium for this game, is 0.4. Alright. So let's look at another agent about how we could learn them. So let's look at this case about here. So here's one we can do here, is each agent can maintain a probability distribution over agents, and each agent maintains an estimate of the doing value A in each other is given the other agent. So this is multiple agents, but here we're going to assume there's just a single state. And so what we can do is you're going to have each agent now as a probability distribution, and each agent also estimates this Q value, and remember there are no states over here. And you can repeat just like we did in reinforcement learning. We're going to select an action using its distribution P. We're going to observe the payoff, and then we're going to update Q. Okay. What we're going to do to update Q is that Q gets to be the payoff, an estimate of the payoff minus Q, and we're going to increment the policy of the best action, and we're going to decrement the policy of the other actions. So it turns out this algorithm here learns how to coordinate, but it's interesting, it doesn't actually converge to Nash equilibrium, it just cycles around one. So it's the case about here, about we have this coordination doesn't converge to Nash equilibrium, but rather cycles around it, because at the time when you get to Nash equilibrium, there's no signal. It doesn't actually matter what you do when you're close to a Nash equilibrium. It's only when you deviate do you get punished for doing it. Alright, that's all. Thank you.